Okay, good morning, everyone. So let's get started. So this is going to be our final lecture of this course. Okay, so then after today's lecture, we're going to have the project period. Okay, so I haven't released the project yet, but I'll do that in a few days. Okay, and you have basically a month to do the project. Okay, so the project will be due after the final exam, which is going to be sometime in mid-June. Okay, so I'm not sure exactly which day it is, but it'll be sometime in mid-June. Right. And the exam, hopefully, the plan is to do the exam in person. Okay, it's very hard to do the exam online, and hopefully the the coronavirus situation has improved by that time, and so we can actually do the exam in person. Okay, so then also after this week, since we're not going to have lectures, I'm going to have office hours. Okay, so I'm going to have like 2 office hours now each week. Okay, so they'll be on Tuesdays and Thursdays. And they'll just be using this program, this Tencent program. Okay, so they're at 5 p.m., 5 to 6 p.m. on Tuesdays and Thursdays. Okay, so then we're going to use this Tencent, and then you can log on and you can just you can ask questions, you can discuss different topics from the course or whatever you need to do. Okay, so I'm going to log on, and you guys can also just log on and talk with me. Okay, so any questions about that? Okay, all right. So then let's do our final lecture. So the first thing is we're going to finish up talking about this list scheduling program that we talked about. Okay, so remember that the problem is that we have a set of jobs, right? And the jobs have certain sizes, and we're trying to allocate them to multiple processors. And we want to finish all the jobs as quickly as possible. So the list scheduling algorithm was just to take all of these jobs and then list them out in any order, any arbitrary order. Okay, and then you just assign and then you just assign them to processors one by one. Okay, just like this this thing over here. And then we prove that if you do this, you get a 2 approximation. Right, the make span that we achieve using list scheduling is at most 2 times larger than the minimum possible make span. Okay, and in fact, we also saw what the worst case for list scheduling is. Okay, so the worst case for list scheduling is if you have let's say m squared jobs, where m is your number of processors, right, and they all these jobs are small, they have size 1, and then you also have one big job of size m. Okay, then if you happen to list them in this increasing order over here, so you list out all of the small jobs and then you list the big job, right? Then we're going to have a big problem because what you see is that we're basically going to allocate the small jobs sort of one by one like this, and in the beginning we're doing very well, right? Because up until this time point we have perfect load balancing, right? So we want all the processors to be load balanced to minimize our make span. And we achieve perfect load balancing all the way until the final job, right? But then we get this final job, which is very big, and this completely destroys our performance, right? So even though we had very good load balancing all the way up to the final job, because the final job is so big, it destroys our approximation ratio, right? It makes it into 2. And so this suggests that what is very bad for us is to put big jobs at the end. Okay, we do not want to do that because it can hurt us in this way. Okay, and so the idea so now we're going to talk about how to improve the approximation ratio for list scheduling, and the idea is simply to avoid this worst case where you have the big job at the end. Okay, so instead, what we're going to do is to put all the big jobs at the beginning. Okay, because for example, if you see that this example over here on the right. Right. All we did was we just did the big job right at the beginning, right? And then after that, you can you can try to achieve load balancing. Okay. So this is going to be the basis for the next algorithm that we're going to talk about, which is called which is called LPT scheduling. Okay. So LPT stands for longest processing time. And so what we're going to do is we're just going to schedule the big jobs first. Okay, because if you put them at the end, it's going to hurt you. Okay, and so LPT scheduling is it's going to take a set of jobs and then it's going to sort them into decreasing order. Okay, you start with the big jobs and then you just process all the jobs in decreasing order, or at least non-increasing order. Okay, and then you just run list scheduling on that sorted list of jobs. Okay, so for example, suppose you get jobs of this size. Okay, now in LPT scheduling, you're just going to take this list and then sort it into non-increasing order, like this over here. Okay, and then you just run list scheduling on this sequence. Okay, so for example, these 3 tasks go to the first 3 processors, right? And then you just keep assigning them using the list scheduling process. Okay, and if you do that, you're going to see that in the end, P1 is going to get tasks 8 and 3, right? And then P2 gets 6, 3, and then P3 gets 5, 4, 2. And then so the maximum make span is for P3 over here, and he has a make span of 11. Okay, which was actually better than the previous list scheduling make span. Okay, so that's the entire algorithm. Okay, take your list of jobs, sort them into non-decreasing order, and then apply list scheduling. And we're going to see that just this very simple variation on the algorithm, okay, is going to dramatically improve our approximation ratio to something to 4/3 instead of a 2 approximation ratio. Okay. Yeah, okay, so let's prove that LPT scheduling actually gets a 4/3 approximation. So what we're trying to do is, suppose the optimal make span is M star, right? And suppose LPT produces a schedule which has a make span of M. Okay, then we want to show that M is less than or equal to 4/3 times M star. Okay, so the approach we're going to use is similar to how we proved our proof for list scheduling. Okay. So again, we're going to focus on a particular job, which is the last job to finish. Okay, so this is the job which determines your make span because it's the final job to finish. Okay, yeah, so just, I don't think I have a picture over here, but if we go back to the proof, right, so this is the picture, okay? So we're going to use basically the same setup as for the 2 approximation. Okay, we're going to focus on this job X, which finishes last. And again, we're going to assume that it starts at capital T, and then it runs for little t, little t amount of time. Okay. All right. Yeah. So okay. So now so now X is the last job to start. Okay. But sorry, to finish. Okay. However, I claim that we can also assume that X is the last job to start. Okay. So not only is it the last to finish, it's also the last one to start. Okay, I claim that we can assume this. And the reason is that, suppose there actually is some other job which starts after X. Okay, let's say Y starts after this time big T. Okay, all right, but we know that Y is not the last job to finish, right? Because by definition, X finishes last. So therefore, Y finishes before time big T plus little t. Okay, and now if you just remove Y from the set of jobs, okay, then you're not going to increase your make span, right? Because Y finishes before T plus big T, big T plus little t. Okay, yeah. So you're not going to increase your make span, and so we might as well just remove all of the jobs which start after X starts. Okay, and we will not increase our make span. Okay, so therefore we can assume that X is the last job to start. Okay, now if X is the last job to start, then we know that X must be the smallest job. Okay, and the reason is that since we're using longest processing time scheduling, then you allocate the jobs in decreasing size, in order of decreasing size, right? So you allocate the big jobs and then the smaller jobs, and then because X is the last job to start, then the last job that you start up is going to be the smallest job, right? Because you start jobs in decreasing order of their size. Okay, yeah, so now we know X is the smallest job, and okay, so we're going to make some claims. So first of all, LPT's make span, right, is going to be big T plus little t, right? Because by definition, X is the last job to finish, and it starts at big T and runs for time little t. Okay, and this big T plus little t we claim is going to be no more than M star, the optimal make span, plus little t. Okay, and the reason is simply that M star here has to be at least as large as big T. Okay, and the reason is exactly the same as for our 2 approximation. So remember there we said that up until time big T, no processor is idle. Okay, because if a processor becomes idle, you simply give it another job. Okay, so therefore, everybody's working up until time big T, and so that means that the total amount of work is at least little m times big T, and so that means that even the optimal schedule needs to take big T amount of time to finish. Okay. All right. So okay. So once we have this claim, now we can prove the 4/3 approximation ratio. Okay. All right. So we're going to consider two cases. The first case is where little t is less than or is at most m star divided by 3. Okay, so little t. So here we're assuming the final job is kind of small, right? It's at most 1/3 the size of the optimal make span. Okay, right. So in that case, LPT's make span is no more than m star plus t, right? And if t is no more than m star over 3, then LPT's make span is no more than 4/3 of m star. Okay, so if the final job is small, then we automatically get this 4/3 approximation ratio. Okay, so the other case is where the last job is larger than m star over 3. Okay, right. But then because we said x has to be the smallest job, right? Because it starts last, then that means that all of the other jobs have size bigger than x's size, which is m star over 3. Okay, so that means that all of the jobs have size larger than m star over 3, strictly larger. Okay, right. And so that means that if you look at the optimal schedule, okay, then you can put at most two tasks onto each processor. Okay, and the reason is because if you look at the optimal schedule, and suppose you some processor actually has more than 2 tasks, so it's got 3 or more tasks. Okay, well, we know that all of these tasks have size at least m star over 3, have size larger than m star over 3. So therefore, if you put 3 or more tasks onto a processor, then that processor is going to finish after time m star. Okay, and so that would mean that your optimal schedule actually has make span larger than m star, which is a contradiction, right? Because we're assuming the optimal schedule finishes at m star. Okay, so that means that all the processors in the optimal schedule have at most 2 tasks. And so that means that the total number of tasks, n, okay, is at most 2 times the number of processors. Okay, so now we're going to consider 2 more cases. Okay, the first case is where the number of jobs is between 1 to m. Okay, so we have basically fewer jobs than we have no more jobs than we have processors. Okay, yeah, and so in that case, both LPT and the optimal schedule, right, both of them would just put 1 job onto each processor. Okay, that's like the best thing that you can do, and that's also what LPT does. Okay. So when n is between 1 to m, then LPT and optimal both behave the same way, and so LPT is also optimal. Okay, and the other case is where the number of jobs is between m and 2m. Okay, right. So in that case, the optimal schedule is going to look like this. Okay, the optimal schedule is to take all of the jobs, and then let's say you sort them in decreasing order, and then you just allocate them to the processors. Okay, one by one like this. Okay, and then next, you're going to take the remaining jobs, and again, you're going to sort them in decreasing order, but then you're going to allocate them to the processors in the reverse order as before. Okay, so what's happening is, this blue job here, or purple, right? This is the biggest job. Okay, this is the second largest, third, and fourth. Okay, and then this is going to be the 5th largest job, 6, 7, 8. Okay, so the optimal thing to do is to pair the biggest job with the smallest job, and then the second biggest job with the second smallest job, and so on. Okay, so you can think about this, and you can convince yourself that this is the best possible thing that you can do. Okay. However, now let's look at what LPT does. Okay, LPT is going to do exactly the same thing. Okay, right? It's going to sort all the jobs and then allocate them to the processors, and then it's going to wait for one of these processors to finish, right? And that's going to be the processor which has the smallest job up to now, right? And then it's going to assign it the next job, which is in this case it's the the 5th largest job. Okay, and then this third guy, he finishes next, so he's going to get the 6th largest job, and so on. Okay, so LPT is also going to produce exactly the schedule, this optimal schedule. Okay, so in both cases, LPT and opt are going to behave exactly the same. And so, of course, LPT is also optimal, therefore. Okay? All right, so what we proved is that if the final job is small, then we just automatically get this 4/3 approximation. Okay? And if the final job is large, right, then LPT and optimal are going to behave exactly the same way. And so, of course, LPT is going to be optimal in that case. Okay? And so, therefore, we've shown that LPT is a 4/3 approximation. Okay, does that, any questions about this? Okay, all right, so then, so then now we are going to talk about one more scheduling problem, okay? So, sorry, I should have opened this beforehand. 1 second. Open with, where is it? Okay, this one. All right, so then, yeah, so then we're going to talk about, oh, this is not the right thing. Oops. Okay, right, this one. Oops. 1 second. Yeah, okay, so then we're going to talk about one more load balancing problem, or one more scheduling problem. Basically, people use these two terms kind of synonymously, okay, scheduling and load balancing. Because if you want to get a good schedule, then you want to balance the load between all the processors. You want to make sure all the processors get about the same amount of load. Okay, so that's why oftentimes people use these two terms interchangeably. Okay, so anyways, we're going to look at a one more scheduling problem. So this is going to be called generalized, generalized load balancing. Okay, and so the setup for this problem is actually is actually the same as for the makespan problem we just talked about. Okay, so again, you're going to have the set of m jobs and m machines and then n jobs. Okay, so I'm not sure why this is so slow here. There's a huge amount of lag, but anyways, yeah, and again, we're trying to schedule these jobs onto the processors, and then our goal is to finish processing all the jobs as quickly as possible. Okay, so all the jobs still have this processing time. Let's say job J has a processing time Tj. Okay, and also each machine can only do one job at a time. Okay, so the only difference, so the reason we're calling this generalized, okay, so the only difference with the previous problem is that now you're not allowed to assign any job to any processor. Okay, each job J can only be assigned to, let's say, specific processors. Okay, so we're going to have a set n sub j for each job J, and you can only assign these jobs to one of the processors in this mj set. Okay. Right, so that is the setup. So, for example, these machines might have, you know, like special data or special security permissions or something like that. Okay, that's why you're not allowed to do just a job on an arbitrary computer. You can only do it on certain computers. Okay, right. But we're still trying to minimize the makespan. Okay. Okay. Yeah. All right. So so we're gonna use some terminology here. So for machine I. Okay, we're going to let j sub I be the jobs which are assigned to machine I. Okay, and in that case, the load of machine I is just going to be the sum of all of the jobs which are assigned to that machine. Okay, so you iterate through the set ji and you add up all of the jobs, their sizes. Okay, and again, we're trying to minimize the maximum load on any machine. Okay, so now to solve this problem, we're not going to use list scheduling anymore. Okay, why is it doing this? All right. This is like a very this program is not written very well. Okay, all right. Sorry, 1 second. How do I do this? Okay, all right, never mind. Okay, okay, so instead, in order to solve this generalized load balancing, we're going to use a technique that we talked about earlier, which is called integer linear programming. Okay, so remember, so we talked about linear programming, which again is to optimize a linear objective subject to linear constraints, right? And then integer linear programming is that not only do you have linear constraints, you also have these integrality constraints, where some variables are constrained to be integers. Okay, and remember that integer linear programming is actually very flexible, very expressive. In fact, you can express any MP problem as an integer linear program. Okay. Now, after you express it as an integer linear program, it is still MP hard. It still might be MP hard to solve that integer linear program. Okay. However, the next thing that you can do is to convert that integer linear program into a linear program. Right. So you remove the integer constraints. Okay. And once you have a linear program, then now we have polynomial time algorithms to solve the linear program. Okay. And so you get a solution to the linear program, but that solution might not have integer values. And so you cannot use that LP solution for your ILP. And so the final thing to do is to somehow convert your non-integer LP solution into an integer ILP solution. Okay. And there are many different ways of doing that conversion from non-integer to integer. Right. And so, for this load balancing problem, we're going to take this approach. Okay, we're going to start with an ILP formulation. You're going to relax it to an LP formulation, solve the LP, and then I'll tell you how we can convert the LP solution back to an ILP solution. Okay. All right, so first of all, how do we express this as an ILP, right? So what we do is like this, okay? So Xij here represents the amount of time that machine I spends processing a job J, okay? All right, so what we want is for each machine to either, so when you allocate these jobs, you have to give the entire job to one processor, okay? You can't give like half the job to one processor and then half of it to some other processor. So therefore, so to capture this fact that you have to give the entire job to a processor, what we require is that Xij is either going to be 0 or Tj, okay, for any j or I. So what that means is if you look at any machine, okay, then the amount of time that it spends processing some job j, okay, is either going to be 0 or the length of that job. And so that means that this machine I either does not process this job at all, okay, or it processes the entire job, right? If it's Tj, then it's going to do the entire job. Okay, so this is how we capture this this requirement. Okay, all right. Next, we have another requirement, which is that remember these jobs j can only be assigned to these authorized machines. Okay, so if you have a job j and if you have a machine which is not authorized for job j, right, then Xij has to be 0. Okay, so machine I cannot process that job. Okay, all right, so and also what we have is that we need to make sure that every job is processed by some machine. Okay, and the way that you express that is that for each job j, okay, we're going to look through all of these machines I, right? And we're saying that if you look at all of these machines and how much time they spend processing job j, okay, the sum of all of these times has to add up to the length of j. Okay, the sum has to be this Tj over here. Okay. And so this means that because these Xij values are either 0 or Tj, okay, then if you require the sum here to add up to Tj, then this means that there must be some machine I in the set Mj which actually processes job j. Right? And so that means that every job gets accomplished by the end. And then the final thing is that for each machine each machine I, okay, the amount of load on that machine is you just simply add up all the jobs assigned to that machine, okay, and then so we want the maximum load to be small. So therefore, we're going to pick a value L, and we want to say that the load on any machine M is going to be at most L, and then we try to minimize L. Okay, so if you find the minimum such L, then that is your minimum makespan, because that's the shortest amount of time where we make sure that all the jobs get finished, right? And all the machines take at most time L, right? And then each job, it gets assigned to exactly one machine, right? And then also the jobs are only assigned to authorized machines. Okay, so the minimum, so the solution to this integer linear program is exactly our minimum makespan. Okay. All right, so then once you have this ILP, right, then you can just convert it to an LP. And when you convert the LP, convert it to LP, all you do is you just take out this single, there's only one constraint over here, which requires integer values. Okay, so you just take that out and you replace it with this constraint, which just says that you don't need to have an integer value over here, you just need to have a non-negative value. Okay, and so this is an LP, and now we can just go solve this LP using a in polynomial time. Okay. Okay, so now we can prove some properties. So the first property is that if you look at the optimal makespan, right, which is the solution to the integer program, okay, then this is at least as large as the largest size of any job. Okay. Now this is so this lemma is exactly the same as so we talked about this in list scheduling, right? Because you have this largest job and you have to give it to some processor, and so that processor will have makespan larger than this maximum job size. Okay, so that's just exactly the same thing. Okay, so next, suppose L is the optimal value to the LP. Okay. Then what we know is that the optimal solution to the integer linear program is at least as large as the optimal solution to the linear program. Okay. And that is simply because the linear program has fewer constraints than the integer linear program, right? Right. So we use this relaxation where here, right, instead of requiring integer values, we just require non-negative values. Okay. In other words, anything which any solution which satisfies the integer program is also going to satisfy the linear program. Okay, maybe not vice versa. Okay, but anything that satisfies IP, it will satisfy LP, and so therefore the minimum for the IP is going to be at least as large as the minimum for the LP. Okay. Okay. All right. So next, we can look at the approximation ratio for this algorithm. Okay. So suppose X is a solution, is an optimal solution to the LP. Okay. Then we're going to form a graph using this LP solution. Okay. And the way we're going to form this graph is that so the solution is just a bunch of these Xij values. Okay, which is saying that does job J get processed on machine I? Okay, and now we're going to look at these Xij values, and they're all non-negative, but we're only going to focus on the positive ones, right? The strictly positive ones. Okay, so if this problem seems like the max flow problem. Yeah, yeah, you're right. So it's going to come out to be very similar to the max flow problem. Okay, so we're gonna see that at the end. But right now, before we talk about the max flow formulation, I want to show how you can convert this LP to a solution to the ILP. Okay, because it's not very clear how that can be done. Okay, but in the end, it will turn out that there's a similarity between this problem and max flow. Okay, so yeah, so let me first continue with this graph, right? So if you have this Xij value, which is positive, okay, then we're going to form a graph where the nodes are going to be the set of all jobs and machines. Okay, so imagine that you take all the jobs, right? You have n jobs and m machines, and then you just make them into nodes. Okay, and now the edges between these nodes are going to be if job j on machine I has a positive Xij value. Okay, then you're going to put an edge between that job node and the machine node. Okay, so for example, you might get a graph which looks like this, right? So all these squares here are machines, and the circles are the jobs, right? And I'm adding edges between, for all these positive values. All right. Now, in general, you could, when you solve this LP and you form this graph, you could just get sort of an arbitrary graph. Okay. In particular, the graph can have cycles. Okay. However, what you can show is that you can also, there exists an optimal solution to the LP which does not have any cycles, which is acyclic. Okay, so there might be some optimal solutions which do have cycles, but there is always at least one optimal solution without any cycles. And so if it doesn't have any cycles, then it looks like a tree. Okay, actually you could have several trees. Okay, so when you form this graph, it can be a forest, okay, containing several trees. Okay, but we can always find some optimal without any cycles. Okay, all right. So I'm not going to prove this fact right now. Okay, so I'll prove it, but I'll leave that to the end. Okay, and this is where the connection to max flow comes in. Okay, yeah. So we'll see that at the end. All right, but we're first of all just going to assume this, and we're going to assume that the graph we form actually is like a tree. Okay, all right. So once we have this tree structure for the solution, then this is how we're going to convert an LP solution into the integer solution. Okay, so what we're going to do is to take our tree and just root it at some arbitrary machine node R. Okay, so like over here, right? We're going to root it at this machine node, this square. Right, and now we're going to start assigning these jobs to the machines. Okay, and the way we're going to assign them is that if you have a job which is a leaf node, okay, so for example, these things on the bottom are leaf nodes, right? Then you know, this job only has a single parent, okay, has a unique parent, and so you simply assign this job to its parent. Okay, right? So you yeah, so all of these leaf nodes get assigned just to their parents. And now for other job nodes, which are not leaves, okay? So for example, for this guy, right? So so now we're going to assign this job to one of its children, okay? So this job actually has multiple children, but we're just going to pick an arbitrary child and assign it to that child, okay? So for example, you assign this guy to the left child, right? This job, you assign it to the right child, okay? You just arbitrarily assign it to one of its children. Okay, so once we've done this, now we have an integer solution, right? So previously, when you have the this LP solution, it might not be integral because, for example, this job, okay, it might have a positive value on this machine and also a positive value on this machine, and that would kind of mean that this job is being partially processed on this machine and then also partially processed on the other machine, okay. But we don't want that. We want each job to be just processed on a single machine. And so we have to just make a choice to assign this job to one of its machines. Okay, and here we just make an arbitrary choice. Okay. Right. So once we do this, we have a correct or a valid assignment to the for the problem. All right. Now we're going to make some claims. So we'll call this solution that we achieve, we'll call that the rounded solution. Okay. So the first claim is that the rounded solution only assigns jobs to authorized machines. Okay. And the reason is that if a job J is assigned to a machine I, right, then that means that there has to be an edge between J and I. Okay. And that only happens when Xij is larger than 0. Okay. However, the only way for Xij to be larger than 0 is that, you see, if you go back to your LP, right, the only way for Xij to be strictly larger than 0 is that J must be authorized on machine I. Right? If J is not authorized on machine I, then Xij has to be 0 in the LP. Okay, so yeah, so therefore, if there is an edge from I to J, right, then J must be authorized on machine I. Okay, so next we're gonna say that yeah, okay. So if you have a job node which is a leaf, okay, and then if I is the machine of that, if a machine I is the parent of that node, okay, then the claim is that Xij here has to be equal to Tj. Okay, so the Xij value is equal to the length of job J. Okay. And the reason is because, you know, if I is a leaf over here, right, then it only has a single parent. And so that means that Xij is going to be 0 for all of the nodes which are not equal to its parent, right? Because if it's positive for some other node, then there would be an edge to that other node. But we know that I only has an edge to a single node, its parent. Okay, so yeah, so I only has a link to its parent, and we know that for I, it has to satisfy this constraint, right? So this constraint is where is it? Yeah, so I has to satisfy this constraint over here, right? Or sorry, the job has to satisfy this constraint. Okay, and so that means that where is it? Okay, sorry. Yeah, so it satisfies this, and since there's only a single I for which xij is larger than 0, then that single xij has to be equal to tj. Okay, if this job was connected to multiple other nodes, multiple other machines, right, then we can't say that any of these xij values are exactly equal to tj. But because because this job, this should be a j here, sorry. Because job j is a leaf, then it's only connected to a single machine, and so that single machine must do all the work for that job. Okay, and then the final lemma is that at most one non-leaf job is assigned to a machine. Okay, and this is simply because if you look at a non-leaf job, so for example this job or this job, right, you just assign it arbitrarily to one of its children. Okay, so you assign it only to a single machine. Okay, so now we can put everything together and we can do our two approximation. Okay, so for each machine I, let's let j sub I be the set of jobs which are assigned to this machine. Okay, right, and so so by the previous lemma, if you look at the load on this machine, okay, it's got two parts. One part is coming from so this machine has certain job nodes which are assigned to it, which it needs to process. Okay, some of those job nodes are leaf nodes, and some of those job nodes are not leaf nodes. Okay, right. So we're going to look at the leaf nodes first. Okay, so so the amount of work that this machine gets from its leaf nodes. Okay, so for example, if you look at this machine over here, right? If you look at just the leaf nodes and how much work is on those leaf nodes, right? Well, this guy has to process all that work. But let's see how large that work is. Okay, right. So what we're going to do is we're going to add up over all of the jobs which get assigned to this machine. We're going to add up all of the leaves. Okay, and we know by lemma 5 over here that because each of these things is a leaf, right? Then the xij value is equal to the size of that job itself. Okay, so we have this equality over here. Okay. And so, so then this thing is, of course, or this quantity here is, of course, less than the sum over all the jobs, right? Because here we're just summing over only the jobs assigned to machine I, and only the leaf jobs. And then over here, right, we're summing over all possible jobs. Okay, right. But this xij, but this sum over here, okay, this is at most L, right? Because this is one of our constraints in the LP. Okay, remember that the LP constraint is, let's go back to the LP constraint, is over here. Okay, for any machine, right? If you add up all the work assigned to that machine, you get at most L. Okay, right. So okay, right. Yeah. So then we have this inequality over here. And then also, because the LP is a relaxation of the ILP, then we know the optimal the optimal L is less than the L star, which is the optimal make span. Okay, so the upshot is that the total amount of work which is given to machine I from the leaf nodes is no more than the optimal make span. Okay, that's what we're trying to show. Okay. All right, so that's for the leaf nodes which are assigned to this machine, right? But there are also non-leaf nodes. So, well, okay, so I guess I should focus on a different one. So let me erase this. Okay, so suppose we're focusing on this machine. Okay, so part of its load comes from these two leaf nodes below it, but another part comes from the parent node. Okay, however, we know that this machine only has one parent node, right? So it only has one parent job being assigned to it. Okay. And so, and we know that the length of this parent job is no more than the optimal make span, right? Because the optimal make span has to be at least as large as the size of any job. Okay, and so that means that the total load on this machine I okay, is simply the sum of these leaf loads, right, which is going to be less than or equal to L star, okay, plus this top thing over here, which is also less than or equal to L star. So that means that the load assigned to this machine here is no more than 2 times L star. Okay, and this holds for any machine, right? For this machine, right, it's being assigned not these 2 leaf nodes. It's being assigned just one parent node over here. Okay, and this guy is less than L star. Okay, yeah. So therefore the rounded solution, right, is a 2 approximation, because the load from both the leaf nodes and from the non-leaf nodes, right, are both less than L star individually. So their total is less than 2 L star. Okay, any questions about this part? Okay, all right, so the final thing we'll do is that we had this crucial assumption that when you form this graph, you get a acyclic graph, right? But a priori, you could have a cyclic graph, right? And so now we need to show, suppose you start with a cyclic graph, we're going to show that you can somehow convert this optimal cyclic graph into an optimal tree graph. Okay, so this is an optimal solution over here, right? And then if it happens to be a cyclic, we're going to show that you can maintain optimality, right? So, but you can convert it to another graph, which is acyclic. Okay, and by maintain optimality, I mean that you can change these xij's to maybe some x prime ij's, where if you plug in these x prime ij's into the LP, you get the same value as if you plug in these xij values into the LP. Okay, so both of these, both the x and the x prime, they're both optimal solutions, but x prime is acyclic. Okay, and the way that we're going to do that is now we're going to look at this previous LP, and we're going to look at it instead as a flow problem, a max flow problem. Okay, so this is exactly getting back to the point that someone made earlier. So the way that we can look at this as a flow problem is that suppose you have a bunch of machines over here. Okay, so we're going to, again, make nodes for both the jobs and the machines. And then you're going to add one more sort of artificial node over here. Okay, so this node is going to have some demand for the flow. Okay, and the jobs are going to have supplies for the flow. And the amount of supply for each job is going to be just the size of that job. Okay, so for each job node, it's going to have supply. Whether or not all the LP problems can be represented by... so are you saying whether you can convert all LPs to flows? No, you cannot convert all LPs to flows. Okay, so I'm not sure what you mean by factor graph, but in general, you cannot convert all LPs to flows, because LP is actually a more general formulation than flows. Okay, but it turns out that for this problem, this problem has a special structure, so that you can convert the LP formulation for this problem into a flow formulation, which is equivalent. Okay. Right? Yeah. So the structure of this problem is that we form this graph over here, and then each job has a TJ amount of supply. Okay. So we have multiple nodes with supplies. Okay. But remember that we talked about variations on max flow, where you could have multiple nodes that have supplies, and also multiple nodes that have demands. Okay, that was the circulation formulation of max flow, right? So we can solve those problems also using augmenting paths and so on. Okay, all right. So then here we have if you have n jobs in total, then you have n supplies. Okay, all right. And so the supplies are going to these machine nodes, right? And each machine node, the capacity of the edge from the job to the machine is going to be infinite. Okay, all of these are infinite. Okay. However, the capacity from the machine to this artificial demand node, this is going to be at most L, or this is exactly L. Okay, right. And so what is this capturing? Okay, what this is saying is that for each job, okay, it must the total amount of work on this job, which is TJ, okay, it must be given to some of these machines. Oh, sorry, I forgot to say that the jobs are only connected to the authorized machines. Okay, so for example, this job over here, right, it's only authorized on the first 2 machines. Okay, every job is only connected to its authorized machines. And so what these edges from the jobs to the machines indicate is that the amount of work in this job has to be done on some of these authorized machines. Okay, right? And also, we want the amount of work given to each machine to not be too large. Okay, so that's why we have this L constraint over here, right? So this L represents, well, if you sum up all of the incoming flow to this machine, okay? And so all that incoming flow has to go out to the demand node by conservation of flow, right? And so this can be no more than capital L. Okay, all right, so we captured two things. One is that all of the work for each job, right, gets sent to some authorized machines. And also all of the total work on each machine is at most L. And so those two properties are exactly what we wanted in the LP formulation, right? If you look at the LP formulation, then those inequalities in the LP just only capture exactly those two properties. And so that means that the LP formulation and the flow formulation are equivalent. Okay? All right, so just give me a few more minutes and then we'll finish this and then we can take a break. Okay. All right, so the LP and the flow are equivalent, and so so the optimal solution to the LP and to the flow are therefore the same. Okay, yeah. So there's this one-to-one correspondence between the LP and the flow solutions. Okay, all right. So now suppose you have a solution to the LP which happens to be cyclic. Okay, now we want to convert it to another solution X star which is acyclic. Okay, so the way that you do that is well, if your LP solution is cyclic, then that corresponds to a cyclic solution in your flow formulation. Okay, so for example, suppose you have, this is your flow formulation, and you have the cycle in your flow solution right now. So this is an optimal solution, but it has a cycle. Okay, and so now we're going to get rid of this cycle. Okay, and the way that we do that is we're just going to cut out one of these cycle edges. Okay, but when you cut out that edge, you have to do something with the flow on that edge. Right? Because currently there's a flow of 1 which is going on that edge from the job to the machine. Okay, and so so the way we deal with the flow is that we're going to reverse the flow. Okay, we're going to send -1 flow on this edge. Okay, so the -1 and the current 1 are going to add up to 0. So now this edge will end up with 0 flow, and so now we can remove that edge. Okay, but now you have an extra 1 flow which is coming into this job, and this job has size 4. So it's got to send out 4 units of flow. And so what you do is if the flow is coming in over here, then you're going to send it out over here. You're going to send 1 unit over here. And so that's going to change this a 3 to a 4. Okay? All right. And so if you send out 1 unit over here, right, then you get an extra unit arriving at this machine. And so that means that you need to take away one of the, you need to take away one of the current flow coming into, 1 unit of current flow coming into this machine, because you need the sum to be no more than 5. Okay, so you have 1 additional flow coming in, so you need to put 1 negative flow over here, and so that will change this flow to a 1. Okay, right, and now you have 1 flow which comes into this node, and now this flow needs to go out from this node also, so it's going to go out from over here. Okay, so this 2 will become a 3. Okay, so then what happens is after you, so we're going to we start over here by pushing 1 unit of flow backwards. And this flow is just going to go through this entire cycle. Okay, and it's going to update the flow on this entire cycle. And after you do that, you're going to get this situation on the right. Okay, all right, and now you see that this situation, now this is acyclic. Okay, I mean, there's a cycle over here, but this is like, remember, this is an artificial node. Okay, so the only nodes that we actually care about are these nodes, the jobs and the machine nodes. Okay, and you see that here, we don't have any cycles. Okay, all right, yeah, sorry, I didn't draw the directions, but the graph is actually directed. Okay, so if you look at here they drew the directions. Okay, so the directions are always from the jobs to the machines to this demand node. Okay, so it is actually directed. Okay, I just didn't draw them. Okay, yeah. So for example, let's sort of do this. Okay, so what we're saying is that there used to be 1 unit of flow going from this job to that to this machine. Okay, but now you want to cancel out that flow, so you're going to send 1 unit of flow backwards, which is going to flow like this, which is going to flow like this, which is going to flow like this. Okay, so when the flow is going backwards, like over here, then what we're saying is that you just decrease the flow by 1. Okay, and when it's going forwards like this, we're saying that you just increase the flow by 1. Okay, does that make sense? Okay. Yeah. And so this way, if you have a solution which has a cycle, right, then you can just push flow along the cycle, and that's gonna cancel out one of the edges, and then you'll remove that cycle. And then if you have more cycles, then you just do the canceling process again. Okay. So you're always taking out edges, so you can never create a cycle through this process. You can only be removing cycles. And so if you do this like multiple times, then you can remove all the cycles, and then you end up with something which is a tree. Okay, any questions about this? Okay, so then let's take a break now. Okay, so it's like 11:05, so let's take a 5-minute break, and then we'll continue at 11:10. Okay. The video. Yeah, so I'm gonna upload them maybe tomorrow. Okay. Yeah, so it's basically to encourage you guys to come to class. Okay. Yeah, I mean the university very much prioritizes attendance. So therefore I highly encourage everybody to come to class, even though this is the last class. So let's see how many people actually showed up today. Oh, okay, 126. Okay, so that's quite good. Okay. I will upload the videos. Okay, but just not the same day as the lecture, but I will upload them in a few days. Yeah, and also if you have questions, then just you can either ask now or this afternoon I'm gonna be logging on to this office hour, so you can also ask that at that time. Okay, or on Piazza or anything. Yeah, so for Tuesday's lecture, I'm also gonna upload that probably tomorrow. Okay. Yeah, so tomorrow I'll put this lecture and Tuesday's lecture on online. Okay. Page 44. All right, 1 second. Page 44. Ugh. All right. Is my mic? Oops. Sorry. Okay. So you said 0 TJ. Oh no. Oh, okay. Sorry, I didn't. Maybe I didn't make that very clear. But no. This is exactly right. Okay. There's no typo here. This is right. So what we are saying, okay, is that Xij has to be either 0 or TJ. Okay. So this is a set, right? A set of two values, either 0 or TJ. Okay, and what that means intuitively is that so Xij is the amount of work done on job J by machine I. Okay, so we want to say that machine I is either going to do all of job J or none of job J, right? It cannot do like half of job J. Okay, so for example, if you had another value Tj over 2 here, right, then you would be allowing machine I to do half of job J. Okay, but we don't want that in the integer solution. Okay, because in our problem, every job can only be assigned to exactly one machine. You cannot split the job among multiple machines. Okay, so therefore this is a set over here. Okay, that's very important. Okay. So let's continue with our lecture. Okay. So we're going to look at one more approximation algorithm. Okay. And this is an approximation algorithm for the knapsack problem. Okay. But it's kind of a new approximation algorithm, which maybe you guys haven't seen this before. So it's interesting. Okay. So all right. So we've talked about the knapsack problem, right? But let me just remind you how it works. So we have a set of items, right? And then each item has a weight and a value. Okay. And then we also have this knapsack, which has some sort of a capacity constraint, big W. Okay. And so now you want to put items into this knapsack, and you need to, the total weight of these items needs to be at most big W. But you want to maximize the value of the stuff that you put in. Okay, so for example, in this example, you might want to put in, these items or something, right? Or actually, yeah, right. So that would maximize your value. Okay, right. Okay, and we are going to, and we're going to assume that all of the items have weight, which is at most W. Okay, and this is because, if you have an item which has weight larger than W, then you cannot ever put that item into the knapsack. So you can just remove those items. Okay, so any item can fit into the knapsack. Okay, otherwise you just don't consider that item. Okay, so there's a dynamic program to solve the knapsack problem. Okay, so let me just, so we talked about this, but let's just sort of remind ourselves how this dynamic program works. Okay, so so what it is that we're going to look at kind of the dual to this knapsack problem, right? So normally we're trying to maximize the value, but now the dual is that we're trying to minimize the weight, assuming that your items have value at least V. Okay, so it's somehow easier to look at the dual than the original problem. Okay, right. So we're going to define a dynamic program where opt of IV is we're only going to consider a subset of the items 1 through I. Sorry. And we require this subset to have value at least V. Okay. However, you want to minimize the weight subject to this value constraint. Okay. Right. So so the way that we're going to solve this dynamic program is that we're going to consider these items one by one, from I to I minus 1 to I minus 2, all the way down to 1. Okay. All right. Now for the ith item, right? So if there's two options. Either you're going to use the ith item, put it into your knapsack, or don't put it into your knapsack. Right. So if you put it into your knapsack, right, then remember we're trying to minimize the weight. Okay. But if you put the ith item into your knapsack, then you increase your weight by Wi right away. Okay. However, now because you put it into your knapsack, then your value requirement is going to decrease. Okay. So previously you need to achieve value V, but after you put this ith item in, then that item has a value V sub I. And so now for items 1 through I minus 1, you only need to achieve value V minus Vi. Okay, so you want to find the minimum way to achieve value V minus Vi among using items 1 up to I minus 1. This is where you use item I. Oh, right. And then in terms of the DP equation, you can write that in this case, we pay a weight of Wi, right? And then whatever the minimum weight to achieve value V minus Vi among items 1 through I minus 1, right? Whatever this minimum weight is, we add that to Wi. And then this becomes our weight for opt IV. Okay, so the other possibility is that you do not use item I. Okay, and then you don't increase your weight, but you also don't get any value. Okay, and so that means that since you're not using item I, then you need to use items 1 to I minus 1, and you still need to achieve a value of at least V, and you want to minimize your weight. Okay, so in the second possibility, opt IV just equals opt I minus 1 V. Okay, and we don't know which one is going to give you a smaller weight, right? It could be this one, it could be either the first one or the second one. And so we just consider both possibilities. Okay, we consider both possibilities, and whichever one gives you the smaller weight, that's the one we're going to use. Okay, and there are also some base cases for the DP, which is that if your value is 0, right, so you don't need to achieve any value, okay, then of course you don't need to spend any weight. Okay, so therefore if v is 0, then the opt is also 0. And on the other hand, if you need to achieve some positive value, okay, however, your I is now equal to 0, meaning that you cannot use any more, you cannot use any more items. Okay, you're only allowed to use items 1 up to I, and here you're trying to not use any items, but you want to achieve a positive value, right? Well, that's impossible, and so therefore you're going to set the the weight required to be infinite to indicate that it's impossible. Okay, all right. So this is going to be our dynamic program, and it's correct. But what we're going to focus on is the time complexity for this. Okay, so for this, suppose there are n items. Okay, and suppose the largest value of an item is v star. Okay, of any item is v star. Okay, then the maximum value you can possibly put into your knapsack is you can put all the items into your knapsack, and each one of them has value at most v star. So the maximum value is going to be n times v star. Okay. All right. So then what we're going to do is because we're trying to look for the minimum weight which achieves any possible value, and we know that the maximum possible value is going to be n times v star, right? Then what we need to do is to solve these subproblems for all the values. So we're allowed to use any item from 1 to n. Okay, so we need to solve all these subproblems for I less than or equal to n, and then also the value is no more than n times v star. Okay, so in total, they're going to be order n squared times v star number of subproblems, right? Just this n times this value over here. Okay. All right, and then and then the solution to the knapsack problem is just what is the largest value that you can achieve, right? Assuming that your weight, assuming that the weight you computed here is no more than w. Okay. And so, so that means that after you solve all of these subproblems, right, you just go, you can compute your optimum value by looking through all of your subproblems, right? When you're allowed to use any items, right, and then you look for all of these v's which are less than your maximum value, right, such that this optimum, right, is less than w. Okay, so for example, if v here is like, let's say it's 100, okay, and then the opt is less than w. Then that means that you can get a value of 100 while satisfying the weight constraint. Okay, and then you check the next higher v. Okay, maybe you check 101, and if you can still achieve it subject to the weight constraint, then your v is going to be now 101, and then you go to 102 and so on. Okay. Okay. So therefore, all we need to do is to solve all of these subproblems, and there are n squared times v star number of subproblems. So therefore, the time to solve knapsack is just order n squared times v star. Okay. Now, this is unfortunately not a polynomial time algorithm, okay, because v star can be very large. Okay. So if we want a polynomial time algorithm, we have to make the running time be polynomial in the input size, but the input size for v star is only log v star number of bits. Right? Like if v star is 1000, you only need 10 bits to express that. Okay. Yeah. So therefore, on this order n squared v star is not polynomial in n and log of v star. And so in order to make this into a very fast algorithm, what we need to do is to decrease this v star here. Okay, this v star is the thing that hurts us. Right? The n squared is already polynomial time. But if you can make the v star small, then you can make your dp fast. Okay, so the type of algorithm we're going to give is called a p-TAS. Okay, so this stands for, did I show this? Yeah, so this stands for polynomial time approximation scheme. Okay. And so the way this works is that for these p-TAS algorithms, you can give me any positive epsilon. Okay, it can be a very small number, like 0.01. Okay, and then this p-TAS algorithm will give you an approximation, will give you a 1 plus epsilon approximation for the knapsack problem. Okay, so if you set epsilon to like 0.01, right, then you get a solution which is only 1% larger than the optimal solution. Okay, if you set epsilon to be 1 over a million, right, then you get a you get a solution which is only like 1 millionth larger than the optimal solution. So that means that you can get a solution which is as good as you want. Okay. However, you cannot set epsilon to 0 because the running time of this algorithm is going to increase. So the smaller you make epsilon, the longer this algorithm will take. Okay, so if you set epsilon to be 0, then this algorithm will take infinite time to run. But for any positive epsilon, right, you can get a 1 plus epsilon approximation, but it will take you more time the smaller you make epsilon. Okay. Now, one thing is that we can contrast this type of p-TAS algorithm with the previous approximation algorithms we saw, which those only achieved like an approximation factor of, let's say, 2 or 4/3 or log n or something. Okay, so those algorithms cannot achieve arbitrarily good approximations, whereas the p-TAS can achieve arbitrarily good approximations. Okay. All right. However, for the knapsack algorithm, the running time is going to be, as I said, it's going to be a function of epsilon. Okay, so it's going to be basically order n cubed divided by 3. Divided by epsilon. Okay, yeah. So that means that the smaller you make epsilon, the larger your running time. Yeah, so we're basically trading accuracy for time. Okay, yeah, so given how much time you're willing to spend, you can try to get the best possible accuracy for that. Okay, so the main idea for this algorithm is to round the solution. Okay, so what I mean by that is, suppose initially you have a knapsack problem which looks like this. Okay, sorry, 1 second. Yeah, so here we see that we have lots of large values. Okay, like the maximum value here is like 28 million. Okay, and so because your running time is like n squared times the maximum value, then on this instance you would need to take something like 28 million time to solve this DP. Okay, all right. And so what we're going to do instead is we're going to convert all of these values to become much smaller values. So for example, suppose you divide all of these values by 100,000. And then you round up. Okay, so the 134,000 is going to become, you divide by 100,000 and round up, it's going to become 2. Okay, this thing is going to become 7, right? And then this thing down here is going to become 284. Okay, all right, so now we have a new instance of knapsack. And the values here are much smaller. So if you solve this instance, right? So if you solve this instance in this amount of time, right? Now it's going to take you like basically order 284 amount of time, instead of order 28 million amount of time. Okay? And furthermore, you can see that these values here are pretty similar to these values over here. Right? I mean, they're scaled down by a factor of 100,000, but they're basically, they're very similar to the initial values. And so that means that a solution, an optimal solution to this small problem, right, should be very similar to an optimal solution to the big problem. Okay? So therefore, our approach to solving the big problem is that we're going to scale it to a small problem. We're going to use the DP to solve the small problem quickly. Okay? And then our optimal solution for the small problem will be similar to an optimal solution to the big problem. And in fact, we can show that an optimal solution to the small problem will be a 1 plus epsilon approximation to a solution to the big problem. Okay? But this depends on which scaling factor you choose. So here we chose like a scaling factor of 100,000. Okay? If you choose a very large scaling factor, this is not going to work. Right? If you choose like 100 million as your scaling factor, then all of these things will become ones. Okay? And then you can't even distinguish between all of these values. Okay? So that will not work. Okay? So you have to choose the appropriate scaling factor. The bigger you make your scaling factor, the smaller these values will become, and the faster you can run. But if you make your scaling factor too large, then all these values are going to become the same as each other. And so then an optimal solution to the scaled problem will not correspond to an optimal solution to the original problem. Okay, all right, so yeah, so then let's figure out how we can choose the scaling factor. So to do this, you first need to decide which what approximation factor you want. Okay, so you get to choose some epsilon. Okay. All right, and then now we're going to set our scaling factor. This is going to be called theta. Okay, so theta is going to be set to epsilon times the largest value, v star, okay, divided by 2n. Okay, yeah, so I should put a parentheses over here. Okay. we must use a ceiling rather than the floor. Yes. Well, later on, I'll talk more about how we do the rounding. Okay. But right now, yeah, we're gonna set the scaling factor to be this, right? And then yeah, and then the way that we're gonna round the values is we need to round up. Yes, that's true. We need to round up. Okay, because later on, to make sure that we have a valid solution, we need all these the scaled values to be larger than the original values. Okay, yeah, so we do need to round up. Okay. All right, so we're going to set our theta to be this thing, okay, epsilon v star divided by 2n. Okay, and then we're going to set these new values. Okay, so these are going to be small values now. Okay, they're going to be equal to the original value divided by the scaling factor. Okay, and then we need to round up. Okay, and now we're going to make a new problem, a new knapsack problem, where each of the original big values is replaced by the small value, this v prime value. Okay. And we're going to call the new problem the scaled rounded problem. Okay, because we scaled it and we also rounded it. Okay, so yeah, so now let's look at what the largest value in the scaled rounded problem is. Okay, we want to make sure this the maximum value is small, right? Because if the maximum value is small, then when you plug it into the DP, you can still run quickly. Okay, so the maximum value in the scaled rounded problem is just going to be the maximum value in the original problem divided by your scaling factor, and then round up. Okay, and so that's just equal to this. Okay, so it's equal to 2n divided by epsilon. Okay, the ceiling of that. And so if you plug in this value into your DP, right? So the DP running time is going to be n squared times this v hat value, and this is going to come out to order n cubed divided by epsilon. Okay, so if you choose this scaling factor, then you get this this fast running time. But the thing we need to make sure is that when you choose this scaling factor, okay, then after you solve this scaled rounded problem, right, then you can convert the solution back into a solution for the original problem. Right? Otherwise, it's useless. Right? I mean, the whole reason we're solving the smaller problem is so that we can use this solution to solve the big problem. Okay? So we need to make sure that our rounded solution achieves a 1 plus epsilon approximation. Okay, so to do this, we're going to introduce a third problem. Okay. And so for the third problem, what we're going to do is to take these scaled rounded values, right? And then now we're just going to sort of scale them back. Okay, we're going to, we divided by theta and then took the ceiling. And now we're going to multiply by theta. Okay, and this is going to produce, so let's say if you start with the value vi, this will produce a new value ui. Okay, and now we're just going to call this the rounded problem. Okay. Because this problem is no longer, because if you look at v and u, they basically have approximately the same size. Okay, so so u is not scaled with respect to v. Okay, u and v have about the same size. However, u is a rounded version of v. Right? U basically looks for the next multiple of theta, which is larger than v, and that's what the value of u is. Right? Okay, so yeah, so we have some properties. So first of all, u is going to be at least as large as v, right? Because here you took the ceiling, right, and then you multiply by theta. So so u is at least as large as v, but u is not much larger than v, right? U is at most theta larger than v. Okay. Yeah. Okay. Right. So the u values are just the v prime values multiplied by theta. Okay. And so what that means is, so u, because it's just exactly equal to the v prime values multiplied by theta, then if you look at the optimal solution when you use these v prime values versus your optimal solution when you use the u values. Okay, so when you have these v prime values, you have one instance of knapsack. And if you use the u values, you have a different instance of knapsack. Okay. However, I claim that the optimal solution for both instances is exactly the same because the u values are just all of the v prime values multiplied by theta. Okay, everything just got scaled up by exactly the same amount. So therefore, whatever is optimal for v prime is also optimal for u, right, and vice versa. Okay, yeah, so these two problems have exactly the same optimal. Optimum. Okay, so yeah, so just to recap, we have three problems. Okay, we have the original problem with the big values. Okay, we have the scaled rounded problem with the small values. Okay, and then we have the rounded problem with also big values, but not exactly the same values as the original problem. Okay, the rounded problem has these u values, which are pretty close to the original problem's values. Okay, all right. So now, we can see how to use a solution for the scaled rounded problem, and we're going to see how to use this to solve the original problem. Okay, because the scaled rounded problem, right, we can solve that quickly using dp, and that solution is also optimal for the rounded problem. And now the rounded problem is very similar to the original big problem. And so therefore, we're going to show that the rounded optimal solution is almost optimal. It's 1 plus epsilon optimal for the original problem. Okay? All right, so let's let S be the optimal solution to the scaled rounded problem, okay, which we can find in time n cubed divided by epsilon. Okay? And so we know that S is also optimal for this U problem, the rounded problem. Okay? And so now we're going to show that S is a 1 plus epsilon approximation for the original problem. Okay, so so what we're going to show is that if you have if S star is the optimal solution to the original problem, right? Then if you do 1 plus epsilon times our value, so we're trying to maximize our value, right? So if you take our value, which is based on the solution S, right, and then you multiply by 1 plus epsilon, then that's going to be at least as large as this optimal value. And this means that our solution S here is a 1 plus epsilon approximation. Okay, does that make sense? Okay, so to do this, we have some like inequalities over here. All right, so the first one is that if you take the optimal solution and you add up the vi values, this is no more than the same set, but you add up the ui values. Okay, and this is just because the ui values are at least as large as the vi values. Okay. Right, and so now we know that when you add up the u values using S star, okay, and you compare that to adding up the u values using S, okay, so this first one is going to be no more than the sum over S, right, and this is because S is an optimal solution for these u values, okay, whereas S star is an optimal solution for the v values, but it might not be an optimal solution for the u values, okay, S is an optimal solution for the u values. Okay, and now you know that each ui is going to be no more than vi plus theta. Okay, so you can replace each of these ui's by vi plus theta. Okay, and so and your solution has at most you can use at most n items in your solution, right? Because you only have n items. Okay, so therefore this thing is no more than this sum of vi over the set S plus n times theta. Okay, so now so now we have some item which has the largest value. So suppose it's the jth item. Okay, so v star equals the value of the jth item. Okay, all right. Then what we know is that so theta was equal to epsilon vj, right? It was equal to epsilon times the largest value, which is vj, divided by 2n. Right? That's how we define theta. Okay, so therefore n times theta is going to be equal to epsilon vj divided by 2. Okay. Right, and this is no more than epsilon times uj divided by 2, because uj is at least as large as vj. Okay, and furthermore, this epsilon uj divided by 2 is no more than this amount over here. Okay, because this uj, okay, so this is simply the amount of value you get by only putting item j into your knapsack. Okay, so you get some amount of value there. So we know that you can put the jth item into the knapsack because all the items have weight less than w. Okay, so you can make some solution using only item j. Okay. However, over here, right on the right over here, we have a solution using all of these items from S. Okay, and we know that this is an optimal solution for these u values. Okay, whereas this thing, which only uses a single item uj, this is just some arbitrary solution for the u values. And so therefore the optimal solution is going to be at least as large as the arbitrary solution. Okay, yeah. Okay. All right, and then now we have this inequality, which just comes from, we said that on the previous page we have that this thing is no more than this thing. Okay, or sorry, it is it's no more than that thing. Okay, so then you just subtract it to the other side. Okay, and now we know that n theta is going to be like this. Okay, so that basically means that if you look at this part, okay, so the sum here is going to be at least as large as n theta times 2 over epsilon. Okay, just the sum over here. Okay, all right. So then you bring that into over here, right, and then you simplify that, and you get this expression. Okay, so we're almost done here. So now we're going to assume that epsilon is less than 1, less than or equal to 1. Okay, because usually you want epsilon to be very small. Okay, and so in that case, 2 divided by epsilon is going to be more than it's going to be at least 2. Okay, and so therefore this quantity here is going to be at least n times theta. Okay, and so what this means is now you have that n times theta is going to be no more than epsilon times the sum of all of these vi values over the set S. Okay, so now we can finally put everything together. So, so from the previous page, we have that the optimal solution, okay, is going to be no more than our solution using these v values plus n theta. Okay, and n theta is no more than epsilon times the solution times our solution's value. Okay, yeah, so this comes out to 1 plus epsilon times our solution's value, right, is going to be at least as large as the optimal solution. And so therefore we achieve a 1 plus epsilon approximation. Okay, so so that's the proof. Any questions about this? Okay, so just to summarize, right, initially we gave a dynamic program to knapsack, okay, but that dp depends on how big your maximum value is. Right? So therefore, we scale and round to reduce the maximum value. Okay, and then you run the dp on this small value problem, and it turns out that the solution, the optimal solution to the small value problem, is actually also very good for the original big problem. And so therefore, we achieved a p-TAS. Okay, and it turns out that so p-TASes are good because you can achieve an arbitrarily good approximation. Right, as opposed to something like vertex cover where you only get a 2 approximation. Okay, and it turns out that for certain problems it is possible to achieve p-TASes. Okay, so for example, so there's another type of scheduling problem where you can get a p-TAS. Right, instead of a 4/3 approximation, you have a p-TAS, and there's a similar problem called bin packing. You can get a p-TAS. And also, there's a version of TSP, of traveling salesman, where you can get an arbitrarily good approximation. Okay, so this is called the Euclidean TSP, where basically you assume that all of these cities in the TSP they lie in, like, let's say the Euclidean plane, okay, or 3D space, Euclidean 3D space. Okay, but some sort of constant dimensional Euclidean space. You assume all these cities lie in that space. And the distance between 2 points is simply their Euclidean distance. Okay, so this is a restricted version of TSP, right? But in this restricted version, you can get an arbitrarily good approximation. Yeah. However, this is not true for all problems. Okay. I mean, there are certain problems where we know that you cannot get a p-TAS unless p equals np. Okay, so you can prove that there are some problems where you cannot get an arbitrarily good approximation. Okay, all right, so so this is all I have to say for approximation algorithms. Now, I just want to finish the course on, so we have a bit of time left, so I just want to finish it on a new topic. Okay, so this is, sorry, let's see. We are using the LP to solve knapsack, whether it means we can solve it. Yeah, well, it depends on what you mean by polynomial time, because our running time, well, anyways, our running time is n cubed divided by epsilon. right? So so if you use a constant epsilon, like let's say 0.01, like 1%, okay, then your running time is just 100 times n cubed. Okay, so that would be a polynomial running time, right? But if you make if you set epsilon to be like a parameter, okay, if you keep making it smaller and smaller, then it's not polynomial time. Yeah, so the answer is that if you fix epsilon to be a constant, then yes, you can get a 1 plus epsilon approximation in polynomial time, and n cubed divided by that constant. Why? Oh, okay, all right. So yeah, so let's go back to this. It's basically because, right, okay. It's because so for the basic dp, right, you get this as your running time. Okay. However, this depends on the value of your largest item, of your most expensive item. Okay. So for example, if your most expensive item has cost like $1 million, okay, right? Well, how many bits does it? So how many bits does it take to write 1 million? Okay. Well, log of 1 million is 20. Okay. So even though the value is 1 million, meaning that when you run this algorithm, it takes you like 10 to the 6 times n squared amount of time. This is your running time. Okay. But your input size is, it only takes you 20 bits to write this number 1 million. So your input size is actually only 20 plus n, right? Because you have like, you need to write n value, or let's say 20 times n, okay? Okay, so this running time here is not polynomial in your input size, okay? Because now, let's say you made this 1 trillion, okay? Well, 1 trillion, now you need 10 to the 12th to run this, okay? However, you'll just need 40 bits to write that number 1 trillion. So basically, this value here is scaling very, very fast compared to this value over here, okay? This running time is scaling exponentially fast compared to your input size. And so this is not polynomial time. Okay, does that make sense? Okay, all right, so so to finish the course, I just want to talk about this, briefly talk about this other topic, which is lower bounds. Okay, so usually I have like a lecture on lower bounds, but this year we don't have time to do that. But I think this is actually a pretty important topic, and so I just want to use a few minutes to briefly touch on this, and then just to show you one lower bound, which you might see this or hear about it in practice. And so I just want to I want you guys to understand where this lower bound comes from, and also why lower bounds are useful. Okay, yeah. So I guess I need to rush through this a bit, but you can ask questions later. Okay. So anyways, so what we're talking about is upper and lower bounds. Okay. So upper bound just means like how much time you need to solve a problem. Okay. So for example, if you have insertion sort, and let's say this runs in order n squared time, then this puts an upper bound of n squared on the time to sort n numbers, meaning that you never need to take more than order n squared time, right? Because you have this n squared time algorithm, so you never need to take more than n squared time to solve a number, to solve sorting. Okay. Whereas if you go for a more efficient algorithm like merge sort, you can sort in n log n time. So this is a lower upper bound now, right? Because you can solve it even faster. Okay. So for upper bounds, we basically want to make the upper bound as low as possible, because that corresponds to solving the problem faster. Okay. Right. Yeah. So for any problem x, if you have an algorithm which can solve x in f of n time, then f of n is an upper bound on the complexity of x. Okay. Right. So that's upper bounds. But now we want to talk about lower bounds. So lower bounds are basically what is the least amount of time you need to solve a problem x. Okay. So for example, if I give you 1,000 numbers, okay, and I want you to find one particular number in that list of 1,000 numbers, and I only give you like 10 steps to do this. Okay, I say that you have to do this in 10 steps. Okay, well that's impossible because you have 1,000 numbers, so you have to look through all 1,000 numbers to see whether the number I give you is in that set. Okay, if you only have 10 time units to solve the problem, you can only look at 10 numbers. So what if it turns out my number is like the 11th number? Okay, then you're not going to find my number. So this basically means that if for certain problems, you need at least a certain amount of time to solve that problem. Right? For this number problem, you need at least 1,000 time units to see whether my number is within those 1,000 numbers. Okay. Yeah. So this is what lower bounds is all about. Okay. What is the minimum time that you need to solve a problem? And so suppose you somehow know that any algorithm, okay, any algorithm which solves your problem has to take at least g of n time, right? Where n is the input size. Okay. Then g of n is going to be a lower bound on the complexity of x. Okay. All right. So, and that means that if the lower bound is very large, okay, then this means that this problem is hard to solve, right? Because, for example, if I can prove that any problem, right, requires, let's say, super polynomial time, okay, right, then this means that it's not possible to solve this problem in polynomial time, right? Any algorithm has to take more than polynomial time, and so this would be a hard problem. Okay. However, in order to show a lower bound, you need to show that any algorithm has to take at least g of n time. And there are an infinite number of algorithms. Okay. So so the only way that you can prove a lower bound, the only way that you can demonstrate a lower bound is you need to give a proof. Okay. You need to somehow prove that all possible algorithms have to take a certain amount of time. Okay. And usually the way these proofs go is that you're going to show that if an algorithm takes too little time, okay, if it goes too fast, then it's going to produce the wrong answer sometimes. So, for example, for finding the number in 1,000 numbers, okay, if you try to do that in only 10 steps, right, then if my number is the 11th number, I mean, not necessarily the exact 11th number, but just if my number that I'm looking for is anything different than the first 10 numbers that you look at, then your algorithm is going to give the wrong answer. Okay, because your algorithm is going to look through 10 numbers, and if my number is not one of them, then presumably your algorithm will say no. Okay, but if my number is actually not one of the 10 numbers you look through, right? It's in the set, but it's not one of the 10 numbers you looked at, then your answer is wrong because you tried to go too quickly. Okay, you cannot go so quickly. Yeah, all right, so that's one point. Okay, so usually we try to show an algorithm which is too fast is going to be wrong. Okay, and also the lower bound depends on the computational model that you work in. Okay, because so for example, if you have a very a basic computational model, so let's say you have a computer which can only do plus and minus. Okay, cannot do like multiply or anything like that. Okay, then in order to solve certain problems, it's going to be very slow. Okay, because multiply is a very important operation, right? If you're not allowed to do multiply, then it's you cannot create large values quickly. And so your computer, which has very limited operations, is going to have a high upper bound. It needs to take a long time to solve certain problems because it's a very weak computer. Okay, but if I provide you your computer more capabilities, okay, for example, I allow you to multiply, okay, then it can maybe solve the same problem faster because it's a more powerful computer now. And so that means that whenever you prove a lower bound, you need to clearly state the computational model that you work in, okay? Because different models have different lower bounds. Okay, and the final thing is that if you have a problem where you have an algorithm with let's say f of n complexity, right, and then you also have a lower bound which is also f of n. Okay, so that means that you can solve the problem in f of n time, and you also prove that you need at least f of n time to solve the problem. Then that would mean that your algorithm is optimal, right? Because you need at least f of n time, and your algorithm takes exactly f of n time, so therefore you have the best possible algorithm. Okay. All right, so so I just want to show you one actual lower bound, which you might see this because it's a very famous lower bound. Okay, so this is a lower bound for sorting in the comparison model. Okay, remember that we need to say which computational model we're working in. So so the question is, suppose you have a computer where you're only allowed to do comparison operations. Okay, so I'll show you what more in more detail what I mean by that later. But basically, suppose your computer can only do comparisons. Okay. Then how many steps does it need to sort n numbers? Okay. Well, we have an upper bound, okay, of n log n, if you use something like merge sort, right? So merge sort only needs to compare numbers, right? It doesn't care what the actual value is. It just needs to take two values and see which one is smaller. Okay, so that's basically the comparison model, is that you're only allowed to take two numbers and see which one is smaller. Okay? And merge sort only needs that operation, and it can sort in n log n time. Okay? And we're going to prove that you need at least n log n time in the comparison model to sort n numbers. Okay, and so this means that merge sort is actually optimal in this comparison model. Okay. All right. Okay. So we're first of all going to have a way to conceptualize this comparison-based model. Okay. So this is called the decision tree model. Yeah. And again, this n log n lower bound. Okay. This is not necessarily valid in other models. Okay. So for example, radix sort can actually work in linear time, right? Because radix sort does more than just comparisons, right? It can actually look at the values, the individual digits of these numbers. Okay, so it's more powerful, so it can possibly go faster than just comparison-based algorithms. Okay, all right. So we're going to look at this decision tree model. So I guess I'll just show you a picture. Okay, yeah. So I don't have much time, so I'll just show you a picture. Okay, so the way this model works is that let me just see what this. Why is computational model made? Oh no. Yeah. Well, I mean, deterministic versus non-deterministic. This is one type of computational model. Okay. But what I mean, in this context, is you need to specify what operations your computer is allowed to do. Okay. So I'll talk about this decision tree model, this comparison-based model. So I'll show you exactly what computers in this model are allowed to do. And this is what I mean by the computational model. Okay, which operations can you do? Okay. Now, in this comparison model is very simple. The only thing your computer is allowed to do is to take two numbers and then compare them. Okay, and then after you compare them, you just get two possible outputs, right? Either the first number is less than the second number, right, or the first number is bigger than the second number. Okay, and then based on that output, you can next choose some other numbers to compare. Okay, you can choose any numbers you want to compare. Okay, but your second choice has to depend on the outcome of the first choice. Okay, so initially your algorithm just arbitrarily chooses some two numbers to compare. Okay, maybe the first and second number, maybe like the 10th and 11th number, or whatever. Okay, so it makes some arbitrary choice, and then after it does that comparison, it's going to get an outcome. And then based on that outcome, it's going to choose the next comparison. Okay, maybe it's going to compare the 20th and the 57th number or something. Okay, but that the second outcome, the second comparison can only be based on the outcome of the first comparison. Okay. All right. Now in this model, you can so if this is all your machine is allowed to do, then you can model the entire computation that the machine performs using this decision tree. Okay, the decision tree is going to start from the first comparison your algorithm does, which is fixed. Okay, and then based on the outcome, the next comparison is also fixed. Okay, and then based on the result of the second comparisons, right, the next comparison is also fixed. Okay, so your algorithm just does comparisons over and over, and each new comparison is based on the outcomes of all of the previous comparisons. Okay, you get to choose what you want to compare next based on what happened before this time. Okay, and at some point, your algorithm can produce an output over here. Okay, so maybe here it did enough comparisons, and it can say that, okay, the order is 1, 2, 3. Okay, so here what's happening is, you do the first comparison, so you see that 1 is less than 2. Okay, and then you do the second comparison, and you see that 2 is less than 3. So therefore, you know the order is 1, 2, 3. Okay, but if you do the second comparison and you see that 2 is larger than 3, right? Well, then now you don't know whether 3 and 1, you don't know which one is larger. So therefore, you need to do another comparison over here, right? And if if it's less than, you get this output, and if it's more than, you get that output. Okay, so that is the decision tree model. Does that make sense? Okay, so let me just give you just give me about a few more minutes, and then I'll finish this entire proof. Okay, right. And so now the complexity of the algorithm, okay, is simply how many comparisons you need to do in your algorithm. Okay, the maximum number of comparisons. So for example, in this execution, right, you only did 2 comparisons. However, in this execution, you did 3 comparisons. Okay, so what you're going to do is to look at this decision tree and look for the longest path from the root to the leaf. And that is going to be your complexity. Okay, so in our case, it's going to be 3. Okay, and what we're going to show is that the complexity of any algorithm, of any decision tree to sort n numbers is going to be at least n log n. Okay, right, so to do that, the key observation is that if I give you n numbers as input, okay, then these numbers can be in any of these n factorial different input orders, right? Like here, for example, if I give you 3 numbers, right, they can be in 6 possible orders. Okay, right, and so given a particular input order, the algorithm, in order to sort, it has to output that order, right? So for example, if I start with some numbers which are in this order, right, but your algorithm doesn't know this order initially, so it has to somehow figure out this order, okay? And in the end, the output has to be this order. Otherwise, the algorithm is incorrect, right? If the numbers are actually 3, 1, 2, but you sort them as some other order, then the algorithm is incorrect. Okay, so given the input order, the algorithm has to output that order. And that means that because you have n factorial different input orders, okay, then that means that your total number of outputs has to be at least n factorial. And remember that your outputs are on these leaves, right? So, so these are your outputs over here, okay? So this means that you have to have at least n factorial leaves in your decision tree, okay? And now suppose the height of your decision tree is h, okay? So the height is just equal to the complexity. So suppose you have an algorithm with complexity h, okay? Then now we have a decision tree which is binary, right? Because each comparison is either less than or greater than, okay? So it's a binary tree. So if its height is h, then it only has at most 2 to the h number of leaves, okay? And yet we know that the number of leaves has to be at least n factorial. Okay, so therefore the total number of leaves has to be at least n factorial, and so the height has to be at least log base 2 of n factorial. Okay, right, and now here I'm just sort of computing what log base 2 of n factorial is, and it turns out that this is going to be omega of n log n. Okay, and so this means that the height of your decision tree has to be at least n log n in order to have n factorial leaves. Okay, and you have to have n factorial leaves because otherwise you cannot output all, because otherwise there is some input order where you do not produce that input order, and so your algorithm is incorrect. Okay, so therefore all correct algorithms have to have height at least n log n. And so therefore this is a omega n log n comparison lower bound in the comparison model for sorting. Okay, does that make sense? Okay, so yeah, so this is sort of the only lower bound I'll talk about. Okay, so there are other lower bounds, but in general, it's actually very hard to prove lower bounds. Okay, so so this comparison model is very simple. So it was actually possible to prove this this lower bound, which is actually tight, right? I mean, this is the correct lower bound. Okay? But in many other models, for example, the general Turing machine model, okay, we do not have good lower bounds at all in that model. Because that model is very complicated, right? You're allowed to do many different things in your Turing machine model, and so it's very hard to sort of mathematically capture what's happening in a computation. And so we do not have good lower bounds in more general models. Okay, so in general, lower bounds are important because they show you you need to take at least a certain amount of time, and also lower bounds can help you highlight which parts of a problem are difficult. Okay, so for example, if you have a problem with several subroutines, and let's say you have 3 different subroutines for your algorithm. Okay, let's say 2 of them have small lower bounds, so they're easy to solve, but one part has a very large lower bound. Okay, so then now you see that this third part is the difficult part about your program, about your problem. Okay, so the lower bounds show you what is difficult about a problem if you can get a good lower bound. Okay, but in general, it's actually very hard to get good lower bounds. So yeah, so that's how it is. Okay, so yeah, so this is the last lecture, and then we have the project after this, which I'll upload the project soon. And then if you want to get in touch with me, then just please come to my office hour. Okay, which is again, it's going to be online on Tuesdays and Thursdays from 5 to 6 p.m. Okay. Will we have a review? We're not going to have an official review, but if you have any questions, you can just ask me directly. Okay. Yeah. Okay. Yeah. In fact, if you have questions now or later, you can just ask me.